First of all, good morning, everybody, and thank you for giving me the possibility to do this online. First of all, I want to just acknowledge the co-authors, the team that is in Politecnico di Milano working on this topic, and the team from OHP Italia and OHP System from Germany that were part of the consortium for the work to build up a demo plant for the carbothermal reaction for the water extractions from simulants, of course, from the lunar soil, and then running the experiments. So very quickly, just to contextualize what I'm going to say, the drivers for our work were to identify a process that was possibly efficient, of course, that allows recycling the products into the reactants, so minimize the mass from the earth, as it is, of course, trivial, that could be scalable up and down, and quite robust and to be automized. So with the intervene of the human beings at the least, so to leave the time for of the astronauts free for others. So it has been said many times in these days, the compositions and the materials that we have as availability from the feedstocks on the moon. So I don't want to spend time on that. I just want to point out that we focused on, of course, the fact that we have quite a large amount of silicon-based group oxides, of course, and we want to work with the dry regolith that is almost everywhere on the surface. So very briefly, just synthesizing the whole, and as it is well known in the community, the focus went on basically two categories of process. One is the thermochemical and the other one is the electrochemical, with the three possibilities that are nowadays quite, let's say, visited by many groups in Europe and not only. That is the hydrogen reductions and the carbothermal reductions from the thermochemical point of view, and the electrochemical, and the molten salts from the electrochemical point of view, with focus, of course, in this case, of the gases that are produced. So the CO, CO2, and the water itself, of course, or directly oxygen extraction. So just comparing some of the criteria that we considered with respect to the hydrogen and the molten, that are those that we are not visited in our experiments. So we focus on the fact that, of course, these are not necessarily limitations, but point to focus on, that we focused on. The first is the limitation on the kind of materials that you can use for the hydrogen, and the results on the yield up to now through testing lab. While for the molten salts, the fact that there are still some criticalities under analysis with respect to the recycling, with respect to the tiles preparation for the electrolyte boxes, let's say. So we made the decision to go to the carbothermal reduction. Why? Because at the terrestrial level is quite well known and there is a high yield. Of course, it works with a molten feedstock because the scope is not the gases collection. It is quite robust, let's say, if we see at the moon, because it's independent from the landing site, as we know. I could work with almost every species, but has the drawbacks to have a high temperature and to have the molten products to be dealt with. So what we did was to focus on avoiding melting, the feedstock, staying with a lower, even if it's high temperature. So we work in the 1200 Celsius, roughly speaking, limiting the moving part. So fluidized the bed, but with no moving, mechanically speaking, parts. So for simplification, to be scalable and to have the possibility to re-inject the products, gaseous speaking, in the cycle, so to be a sort of almost closed loop. So this is the scheme of the plant somehow. So we have one cycle of the carbothermal reduction with a mixture of methane and hydrogen that is followed by a Sabatier reaction to arrive to the water. But in the carbothermal reduction, we alternate fluxes of the mixture of hydrogen and methane and a washing phase with hydrogen only to facilitate the CO and the coker removal fixed on the particles and have pristine materials to work with again. So you see the main reactor to get the CO and CO2, the methanation to get to the water, and then the condenser, of course, to separate the interesting product to the waste that are then in principle recycled. The experiments that we did so far has no recycling, but the work that we are doing so far identified a way to, and we are preparing the breadboard in the lab for doing also the recycling of the exhausted mixture. A snapshot on what we did. So we run in parallel, thanks to the support of the European Space Agencies, the numerical identifications and then verifications of, first of all, the thermodynamics, but then also the chemical kinetics, both for the main reactors and for the methanation. So for the second stage to get to the water. And here you have some snapshot of the work done left to right, numerical and modeling up to the finalizations of the plant. And then I would like, of course, to run to the experiment. So this is the plant. Of course, is not the scale to fly. The scope and the goal was to manage at the maximum 1 kilos of simulants. So everything is COTS, just the condenser right part of the slides is a custom done in lab. And we have the main furnace, 1200 degrees with the feed salts and the fluxing of the two gases and the washing when we do just the hydrogen. Then of course the rack with everything for the control, the methanation furnace, 250 degrees for activating the process, and then the condensation at minus 50 degrees in a fridge. Of course, we characterize our simulants. We work at the most with islands, so nothing peculiar to say, just to show you that we went through the mineralogic characterizations, the DSC for understanding the melting point and staying below, the feasibility of that with some TGA tests before, and then of course also a bit of flowability for charging and discharging the reactor before and after the process. Now getting to the results, that is the most important part. Sorry. These are the sensitivity analysis that we conducted. So on the simulant mass, on the mixtures of the gases, on the temperature, of course, and then in the second bunch of experiments, the ratio between the simulants and the gas that was quite fundamental, the durations of the single batch, the fluidizations, and whether we need a beneficiations or not. So in synthesis, in this table, you can have and you see synthesized all the parameters that we tuned and how. So starting with a smaller mass, getting to the kilos, and then coming back to a very few tens of grams. That was the best results that we got. We couldn't control the let's say the increase of the flux of the gaseous reactant, and so to analyze that point, we reduced the mass, and we found out that was really beneficial. And at the very right part of the table is the result that is the most interesting. So the recovery yield with respect to the overall mass of the feedstock, and the recovery yield with respect to the oxygen that was present in the pristine feedstock. I just reported an example of one batch evolution with different color lines that represents different tuning that we did, just to highlight the effects on the concentrations of the main reactor output, that is the CO, that is then the trace of having the oxygen, the water at this point, because we didn't put the electrolysis afterwards, but the water that we got. And you can see the negative slope in the mixer part for the carbothermal reduction, and at the end of it, the fluctuations of the hydrogen only. And when you see this step is, of course, the mixture starting again. And so the step, let's say, witnesses the benefits of having the fluctuations of the hydrogen to recover the concentrations, and starting, of course, with decreasing peaks, but higher with respect to the end of the fluctuation. So what I would like to show the more in this chart, the rest is the same, just concentrate on the, I'm finishing, on the graph, the effects of the hydrogen fluctuation. So it is important to have an hydrogen fluctuation quite long with respect to the mixer that is beneficial for the results. So getting to the very final slides, so that to be fast. This is the visualizations of what we get in terms of water, and the fact that the wasted material is quite fluent, so easy to be discharged. And with that, we also run, not at the level of the former speaker, but we run some laser selective laser melting techniques for 3D printing that gave good results, as in line with what has been presented before, just small bricks that we produced and we tested in terms of strength, as mentioned before. Beneficiation, we did some tests also selecting the grain size, but as you can see from the graphs, there is no significant variations in the yield. And so this confirmed that the beneficiation is not needed with this kind of process. It's just a matter of a long time. And I'm concluding saying that, of course, the test allows us to confirm what we expected from the theory and the numerical modeling. What we have in mind to keep on going is to do with the recycling, as I told you before. So we are in preparations of the breadboarding for that part, because we identified the technology. And we also are starting working with a scaled plant to demonstrate it possibly also with flight. So I ended up. Thank you for your attention.